These are some of the topics where we are involved in research, starting from time synchronization in 5G wireless communication systems, ultra-reliable front-haul solutions, then machine learning methodologies in optical communication systems, and 5G wireless communication and health effects. So just giving you a brief overview that our collaboration is all over the world. We are linked with not only Pakistani universities like NAST, Khwaja Faiz University, in Rahim Yar Khan, but also with other universities like in UK, in Europe, and even in US and Canada. So let's start the topic, and we can also have a change in this format, but what I propose is that we start with the basics about what is 5G, how it works, its different protocols, what is the technology where we are going to discuss today. Then we will talk about the topic of interest, which is the radio frequency transport using sub-6 gigahertz fronthauls. We'll talk about research activity 1 and 2, and then maybe we can have a 5 minutes of break, and then we can rejoin for the remaining part, which will be about the deep learning for MIMO, digital communication, FPGA-based embedded systems, and finally the joint thesis supervision topics and collaborations, if we can have some understanding there. So I would like to start with the evolution of communication. That communication has evolved over the years, and if you see in the start, we had fire that was used as an indication of signaling for keeping the people alert. For example, Wall of China, they used to use the fire to alert people when there was some incident or if there was a war. And then finally, the lighthouse was used for the signaling. And then over the years, Samuel Morse, who invented Morse code to finally have the transmission over the power cables for the telegram that we know nowadays, was the evolution of communication. So communication has evolved over the years. And if we look back, the first transatlantic communication, the pioneer was Guglielmo Marconi, who succeeded in sending the first radio transmission across the Atlantic Ocean. And he actually disproved his detractors who told him that the curvature of Earth would not allow this transmission and it will be limited to 200 miles or less. So basically, because we are talking about 5G and we are looking at how it works, so I have added a little animation here to explain all the audiences, especially the students who have joined us, that how this is evolving and how it works. So let's have a look at how the generations have evolved. So for example, you're seeing that to understand, you need to understand that where it all began. So first generation of wireless networks got us started with phone calls, some text messaging, and eventually the mobile web, that is 3G. And then we came to 4G that got us video chatting, ride sharing, social networking, and using apps for everything. And now with the generations that came before, 5G will change our lives in all sorts of unexpected ways. The 5G networks are live across the country, all over the world, and they'll continue to improve the coming years. And they will be 100 times faster. And they will put high-speed broadband in the palm of your hand, and that will connect not only the streaming of pictures, perfect up to 4K videos, but they will download whatever you want and whenever you want instantly. But speed is not the only thing that 5G will offer. 5G will be 5 times more responsive than today's network, and that will connect 100 times more devices. So this means that phone will not only be the smart wearable that you will carry. So that will connect driverless cars in communication, avoid the accidents to road buildings. We can have the bridges and pipelines to tell the repairs. Then the augmented reality, which is a new field, and then the new healthcare models will evolve. With these new healthcare models evolving, the patient monitoring and remote surgeries will happen remotely. So we are only just beginning to imagine that what possibilities 5G will evolve. So this is not only limited to the speed, but for instance, for explanation, we can say that the difference that will create in the market will be the speed that we will see. So to summarize what we have seen in our animation, it is it is not only the number of subscribers over the amount of traffic, but it is also the efficient network that 5G will provide us, offering the higher data rates, efficient signaling. Not only the network coverage will be wider, but also the device battery life will be prolonged. So these are some of the advantages that 5G will bring. So now, because we are talking about communication perspective and 5G, so it is right time to tell the audience that what exactly we are going to talk now. And it is important to show you another animation to explain you that how communication has evolved and what exactly we are talking about in today's world. So this is the animation that you will see. Right now, we will explain this, and this is the topic that we are going to discuss in detail then. So as you know that mobile phone is part of our lives nowadays, and your curious mind will always be struck by a question that how mobile phones work and what are these different generations. As we have seen before, in that the data rate is not only the reason. So let's explore the technology that is behind mobile communication. So when you speak in your phone, your voice is picked up by the phone's microphone, and this is converted into the digital signal with the help of the MEMS and IC sensors. So the microphone that you speak with, it converts the signal into digital form in form of zeros and ones. So the antenna inside the phone, what it will do is that it receives these zeros and ones and transmits them in the form of electromagnetic waves. So these electromagnetic waves transmit the zeros and ones by altering the characteristics such as amplitude, frequency, phase, or combination of these two. So for example, in case of frequency, 0 and 1s are transmitted by using low and high frequencies as you can see in this animation. So if you could find a way to transmit these electromagnetic waves to, for example, your friend's phone, you will be able to establish a call. But the problem is that electromagnetic waves are incapable of traveling long distances, and they lose their strength due to physical objects and electrical objects such as refrigerators, microwaves, and other surroundings such as environmental factors, rain, etc. Even if there are no such issues, even then you cannot really transmit electromagnetic wave due to the curvature of the Earth shape. So to overcome this issue, cell towers were introduced using the concept of cellular technology. So in cellular technology, a geographic area is divided into hexagonal cells, with each cell having its own frequency set. So this frequency slot generally has a cell tower that is connected through wires called as optical fiber cables. And here is what we are involved in our research. So these optical fibers are laid under the ground, over the ocean, all over the world, and they connect it internationally and nationally. So the electromagnetic waves produced by your phone are picked up by the tower in your cell, and they convert them into high frequency light pulses. And these light pulses, as you can see in the video, are then carried to the base transceiver box located at the base of the transmission. And then they are carried for further signal processing. And then after processing, they go to the destination tower. So when this destination tower is received by the tower, it converts these pulses into the electromagnetic waves and radiates it to your friend's phone. So this signal undergoes exactly the opposite that happened earlier, that it converts now the digital signal into the analog signal. And then your friend or someone who's at the receiver end can receive the pulses and can see the electromagnetic. With the help of electromagnetic radiation, with the waves, they can hear the signal that was transmitted. So it is correct to say that it is not only the wireless medium, but also the wired medium that plays its role in mobile communication these days. So now, as we have seen this animation, it's a good point to really start the webinar with the explanation about the topic that we are talking. And we are talking about radio or fiber. So when we say that light was being modulated in the pulses from the tower and it was going through the signal processing that you have seen earlier, that is the point is in this block diagram where you see that this light, this laser diode is RF signal is being modulated by this laser, and after being converted into the light pulses, it is being carried by this optical fiber, which is the optical medium, the transparent channel, to transfer the RF signal from one point in time to the other point in time. And then once you receive it, you convert it back into the RF signal by the photodetector, which is at the receiver side. So this is basically a way of transporting radio signals from one point to the other using the transparent channel while you minimize the nonlinear signal distortion and system noise figure. By system noise figure, I mean that all these components will have nonlinearity. So these nonlinearities will add their part to create the system noise in the overall scenario of this link. Now, there are different techniques by which you can do this transportation of radio frequency signals. You can do it in analog form, you can do it in digital, and you can also do it with sigma delta direct modulation and red detection. So advantages, as you have seen in the slides and the animation before, it improves the wireless coverage. This is tolerant to electromagnetic interference. The waveform is preserved. We have less fiber attenuation in the fiber. The data rate is high. That is why that when you see nowadays, even in Pakistan, that we have the fiber to the premises, there are a lot of companies who are offering now the optical fiber communication systems to the fiber to the premises and home, FTTP and FTTH. That is why, because they have higher, they offer better communication system and higher bandwidth. And then finally, if you see it from the perspective of cost, these small cells are economically viable. By economical viability, I mean that when you have a lot of radio access points, and that way the base station can serve a lot of RAPs, that is the radio access points. So you can rely on the centralized signal processing for all of these base stations. What you have seen previously in the animation, this is just a block schematic diagram to explain you that generally you have a 5G core network. You have the centralized office for the signal processing. This is the backhaul, and then this is the optical front haul that we are involved in. So this optical front haul that connects your centralized office to different remote radio heads, the towers, is actually the radio or fiber. That can be analog, digital, sigma delta, whatever you name it. So in this way, you are extending the coverage of the network, not only through the wireless medium, but also through the wired medium. For example, in stadiums, in railway tunnels, in sports stadiums, even the huge buildings nowadays with the supercell and all those, they are being used in this communication. Now, the first point that we are going to discuss in this webinar is that why we are relying on analog radio or fiber. By analog, I mean the simplest form that you have seen previously in the block diagram. And we start with that system of radio or fiber. The reason is that they have low modulation and detection bandwidth at the electrical, optical, and optical electrical stages. That is the laser side and the photodiode. And then the remote antenna units that are at your private houses, so they can be placed in your domestically, and they are simple and inexpensive. And then also a very big factor is that the legacy infrastructure. Analog ROF is already available all over the world. So instead of using a new technology and paying for that, it is better to use analog and solve the issues that are linked with this technology. So before, as you've already seen, this is the block schematic diagram of analog ROF. And it is inexpensive, it is economical, yes, but there are some issues. The first issue is that its performance is limited by the modulation response. by that I mean that there are non-linearities linked in these components. For example, laser diode has non-linearity. Fiber has its attenuation. By attenuation, I mean the loss of signal when it travels through the optical fiber. And then photodiode converts the optical signal to electrical, so it has also some issues. Then the dominant distance that you can cover with this communication system is only tens of kilometers, maybe 20, 30, 40. And when you talk about radio or fiber, you are talking about hundreds of kilometers. So over there, you lose your interest in analog ROF. And now, and also now between the 5G and beyond 5G networks, it is actually very challenging to track and compensate the nonlinear response that is being done through multiple radio access points. However, we take analog ROF and we would like to solve the issues that we have with this technology. And the nonlinearity issues are basically listed over here. That when we talk about LTE, long-term evolution, and LTE advance, we know that they are using the OFDM, the orthogonal frequency division multiplexing, and they are actually susceptible to high peak to average power ratio, that is PAPR. So basically, it is based on this optical subcarrier modulation. So the basic nonlinearities that can be divided in the system are combined effect of laser chirp and fiber dispersion, and the nonlinearities of laser diode and other nonlinearities. So basically, we would like to compensate the first two highlighted parts, which are the combined effect and the nonlinearities of laser diode. So here I have summed up that actually, if you suppress these nonlinear distortions, that is, if you linearize your Fronthauls, that is the successful application of the broadband Fronthauls actually in the transmission of radio over fiber. So if you can linearize your system with this inexpensive link, you are good to go. So what does it mean? It means that there are different technologies and different techniques that has been developed over the years for linearizing the system. And one of them is digital pre-distortion, that is part of electrical and digital side. Now, I will not discuss in detail that why digital pre-distortion, but I will just comment that because of simplicity and the less complexity of the system, digital pre-distortion always prevails over the other offers. So that is why the DPD or digital pre-distortion is used. So let's suppose you have this radio over fiber. Let's say this is a black box, and we don't care if the nonlinearity is because of laser or fiber or photodiodes, but we have an overall response of the ROF, which is something like this. And we want to make it very linear, like y is equal to x. So if this is nonlinear, I want to make it linear at the output. What I can do? I can try to cascade a system with this ROF, which is inverts in response to this response in the power output to the power input. So if you have a response which is something like this, so in that way, when you will combine this ROF response with this non-linear inverse response, the overall output will be very linear, something like this that is drawn over here. So that is the reason that we have tried to come up with this explanation that if you cascade a DPD, which has a response inverse to this radio over fiber, and you cascade these two systems, then the overall response will be very linear at the output. Over the years, there are different methodologies that have been developed in DPD. One of them is the dynamic range enhancement technique, adaptive compensation, machine learning methodologies that have been evolved over 2-3 years in the last decade, and behavioral model techniques. So today we are going to talk about for the last 3 techniques that we are talking about. And the first one out of them is behavioral model technique. Why behavioral? Because when you will see the adaptive compensation and then finally the machine learning techniques, you will realize that how with the time this DPD methods have evolved, and we are getting better and better in performance. So first of all, we are talking about the behavioral model technique for the DPD in the long haul ROF links. So basically, you have a radio or fiber. We take it as a black box, and we have a DPD predistorter, and we believe that we have a current IRF that goes inside the predistorter, and that predistorter will give me a correct IRF, and that will excite my radio or fiber, and the output that I will get, it will be without any non-linearities of laser amplifiers, photodiodes, fibers, whatever. So it's like a black box technique. And the technique that we proposed actually depends on just one parameter of the laser, which is the transient chirp. It is the coefficient. When you see the documentation of any components, you can see that there is a list of different parameters, and KT, the transient chirp coefficient, is already given there. So this behavioral model is based on the parameter that is already available in the documentation. So if you see it from the mathematical point of view, I will not go much in detail in explaining all the blocks, but just to give you a flavor that how it is done, we have a laser, we have a fiber, and then we have photodiode. So let's suppose that we have the coefficients transient and chirp and adiabatic. These are the two coefficients that are the part of the laser. And we have a field, and then we excite it, and then we have a fiber. So the issue is that this I of t that goes inside the laser and the pin at the photodiode, the I out is full of nonlinearities. It is full of the distortion terms due to chirp and dispersion. So the problem is that we would like to model this system so that this I out is without any issue. And for that, we came up with an idea of using a dispersion compensation function, which is actually just the inverse conjugate response of the just like the conjugate response of the pulse response of the fiber. So now the idea is that once this I of t goes inside the laser, it gives me the field, which is E of t. And when this E of t field goes inside the compensation function, this will give me correct E core. This is the correct field, E core. So instead of having E of t to excite my fiber, I will have correct field that will go inside my fiber. And I believe that once this E core will go inside the fiber, my E out that will go inside the photodiode will give me correct current. This means that just by having this dispersion compensation function, you're actually negating or reducing the effect of fiber nonlinearities that are due to the chirp and fiber dispersion by just having the conjugate response of the H of t. So it is correct to say that the corrected E core goes into the input, goes inside the fiber, and the output current I core that will come out of the photodiode, this will not exhibit any chirp or dispersion. So this is actually easier to see in the digital implementation of the idea that you have an I of t, you have the sampling, you have the field, then you find the correct field, you have the correction of the current that goes inside the laser, and then this laser inversion, when you excite it through the photodiode, at the laser output, you expect that the correct field will be emitted. So basically, this is a laser inversion procedure that you're looking for, and you're determining a current I core, which will assure that the phase that it will generate will be equal to the phase of the wanted field of the correct field, which is E core. And this is actually a very simple mathematical expression that I core is actually equal to phase of the field. This is the phase of the field divided by this chirp coefficient, which is given in the documentation of the laser. So once we have this, we are good to perform our behavioral model. And in the next slide, you will see, before I go to the results, I just want to highlight, because we use these two parameters, adjacent channel leakage ratio, ACLR or ACPR, and error vector magnitude. So it's good to explain these quantities, because we will use these quantities again and again in the results that we will see in the next slides. So generally, when you have the main channel, you have the adjacent channels, and because of the IMDs and distortions, the channels that are adjacent to each other, they create distortion terms. And what you do is that you measure this distortions by a quantity called as ACLR. That is actually the power in the adjacent channel to the ratio of the power in the transmitted channel. So these are the adjacent channels, and this is the transmitted main channel. And the other quantity is error vector magnitude. So just consider that you have constellations. If you have studied the BPSK or quadrature amplitude modulation, or even QPSK, quadrature phase shift keys, these these modulation that you generally read in your undergrads. So let's suppose that you have a transmitted constellations and you have the received constellation. So then once you have the transmitter and receiver, you compare the constellation transmitted and received, and you try to find out the vector magnitude of the error that they're producing to each other. For example, here, this is the measured signal, this is the received one, and this is the reference, which is the transmitted one. And then you can find the error vector between these two that we generally used to find in our high school. So this is the error vector between the two transmitted and the received constellation. So that is called as the error vector magnitude, and it is generally used to find as a performance matrix of the system. So just to give you the idea that what is ACLR and EVM. So when you find the ACLR, you have two possibilities, that you are comparing the results without DPD, that is without digital pre-distortion, without linearization, with linearization. So uncorrected stands for without DPD, and with DPD means with linearization that we have performed. So if you see that we are at a very high power of -50, -60 dBc here, and with the performance correction that we have done, we are around -90. So in the negative scale, you see that we are actually suppressing the leakages in the system. So if you see it in this way, you can see very clearly that for the very strong coefficient, which is the adiabatic one, when you compare -20 of the uncorrected without DPD with -30, for 10 dBs of improvement is a lot when you see the adiabatic chirp coefficient, which is around 450. Generally, we are working somewhere here, 240 to 220. So even there, you can see that the improvement is around 10 to 15 dBs. But it's good to see these results in form of spectral regrowth, which is to see the spectrum of the output, which is the power spectral density, PSD, or spectral regrowth, we call it, and you compare that how your uncorrected behaves with respect to the corrected one, the DPD one. And it is more visually, let's say, clear that over here, the blue curve, which is the output without DPD, has higher spectral regrowth. And with this technique that we have developed, you're able to suppress the regrowths and the leakages in the adjacent channels. So we are good, and we can see that we have a good improvement here. Also, if you see the EVM, which is the error vector magnitude, you see that without DPD, the constellations are very noisy. While if you see the correction here, the corrected constellations are very clean. So you are improving and getting better and better constellations. The next thing is the adaptive compensation technique. We have discussed behavioral model in the first step, but the problem is that it is very mathematical. It has some limitations because you are using it for the long haul rough link, means for long lengths. And it is also it is difficult to realize because you depend on the complexity of the system that you're using, the machine that you're using. So there is another technique that was developed using the adaptive compensation for the short range, which is for short lengths, like that used in buildings, in submarine applications, let's say in small lengths, for example, in the community around your houses or others. So that is called as the short length, like for maximum of 1 kilometer of link length. And here we know that laser is the main source. We know that when the length is small, fiber has no effect of nonlinearity. The only source of nonlinearity is laser. So in that case, there is another technique that we have developed, and that is called adaptive compensation method. I will not go in much of the explanation of mathematics, but just to show you that it is coming from the Volterra series that is being used in this signal processing. So you have memory polynomial and generalized memory polynomial. So in memory polynomial, you have the coefficients a, k, q, and you have the nonlinearity order k and memory depth q. While in generalized memory polynomial, you don't only take the diagonal terms of the matrix, but you also take the leading and the lagging term. So you just don't rely on the diagonal matrix, but you take the leading envelope, that is q minus r, and then the lagging envelope, the q plus r, or vice versa, the lagging and the leading. So these are the two architectures that are being used in adaptive compensation. And then there is another idea of using decomposed vector rotation model, which is not Volterra, but it is coming from the canonical piecewise linearization, CPWL. So the idea is similar over here, even that instead of using Volterra method, why not rely on another architecture which can perform better linearization? So I'll just skip the mathematics just to show you that this is also something like Volterra, but not exactly coming from the Volterra series. So if you talk about this method of explanation, it is good to explain this block schematic diagram, that how we do it. So let's suppose that ROF, that laser, fiber, and photodiode is a black box, and that is present over here in the radio fiber system over here. And then we are talking about dual channel or multiple channels. Why? Because with the increase in the complexity of the systems with the 5G and beyond 5G, the single channel is explanatory, is good, but let's rely on a dual channel or multiple channels. So it's good to explain that how the multi-channel works. So by multi-channel, I mean more than one signal traveling. So let's say we have Y1 at the receiver output and Y2 at the receiver output 2. And X1 is the transmitted signal X1 and X2 is the transmitted signal X2. What we want at the end of the day is that this X1 is very close to Y1 and X2 is close to Y2. But because of the nonlinearities and issues that we have, X1 and Y1 are not same, and X2 and Y2 don't match each other. So then we need this system to create a system to make this X1 and X2 close to Y1 and Y2 respectively. So after the gain adjustment, because there are amplifiers here, EDFAs, optical amplifiers, so we try to adjust the gain and try to bring it back to the normal level by using the adjustment gains here. And then we bring this Z1 and Z2, which are actually Y1 and Y2 with the gain adjustment, to our system that we call as the training block or the pre-distorted block. So what we do here is that we use memory polynomial, generalized memory polynomial, or DVR, different architectures, let's say, and we try to train our signal that is received so that it is close to X of n, which is the transmitted one. And unless my error, which is the reference signal that we have chosen, let's say some value, it doesn't, the coefficients are not close as much as possible to the transmitted signal, it keeps on training. So for example, we have Z1, we have X of 1, we train something, we have ZP of 1 as output, so we compare ZP1 with X1, and we see that the error is still not good, which is E1 is still not less than the reference. So we again go to the training block of MPG, MPDVR, and we again train here. Similarly for ZP of 2, we see that MPGMP for Z2 is not close, and E2 is bigger than the reference that we have set. So we keep going on training. Once the training coefficients have learned and the coefficients have trained itself, we are good to go, and we place this training block as the pre-distorted block. This is the indirect learning architecture, ILA, that is used in the theory that we're using over here. So once your training has converged with respect to the reference error that you've set, you are good to perform the linearization. That is the DPD block that has been trained here and the ROF system. So this is the experimental setup, just to show how it works. This is the ROF system, which means that there is a laser. You have a biasing T here. You have a DC current generator so that you can bias this laser. You have a fiber length. You have the photodiode. Then you have a signal analyzer. With this signal analyzer, we have MATLAB-based. We had, not now. Now we have a signal analyzer which already has all these type of communication systems. but at that time we implemented the MATLAB-based LT receiver. So you have channel 1, you have channel 2. So for instance, you are using channel 2. So you receive the channel 2 output, and then you bring it to your offline MATLAB processing block, where you measure the minimum mean square error, or ACPR, that we discussed, the adjacent channel leakage ratio, or error vector magnitude. Once you synchronize it, you train the system, the training block that you saw in the previous slide. You have the digital pre-distortion output. You see the reference so that you can time synchronize it with the reference block that we have. And once you perform this DPD, you provide your output coefficients of the DPD to your signal generator with the help of this LT frame generator that is implemented in MATLAB. So with this, you provide it to the VSG, which is a signal generator, and this signal generator uploads a new signal, which is DPD based. The coefficients are updated to this link, which is ROV system. And then at the output, you receive and compare the results of the ACPR and EVM with and without linearization that you're performing. So there are some, let's say, parameters. VXL is the laser type, QAM modulation is 256, 10 megahertz LT signal, and multimode fiber of 75 meters length. So when we compare the results with respect to ACPR and EVM, you see here that the two channels, the blue one, red and green, these two channels have different behavior because they are two different frequencies. They are operating at different frequencies, but same length. So for example, this is at -20, -25 dBc, which is a very high value at 0 dBm of RF input power. So from -25 or -20, we are reducing with our architectures proposed like DVR or GMP to around -40. And one may ask me that why you went to DVR. So the answer is that GMP was performing up to -30 dBs. The improvement was 10 dBs only. So we tried to come up with a new architecture and a better performance enhancement, and that was done with DVR, which is actually outperforming it by around 25 dB. So it's -40 and -25, so 15 dBs. We have reduced from -30 to -40 dBs. So that is the reason that DVR was used. And then you can also see that not only in one performance metric, if you even see the EVM, from 7%, we are around 3% here. And mind you that the limitation set by the 3GPP is a third generation partnership project. This is the International Telecommunication Unit, ITU, where all the consortiums and all the companies and all the stakeholders meet and they decide the values set for the system level or link levels performance indicators. So 3GPP has set a 256 QAM limit to be 3.5%. So you can see that we have to reach 3.5% if we have to be standardized according to the industry. So from 8%, which is not acceptable, you are just at the border of 3.5%. So still there is a chance that with some other architecture or other technique, we can beat this. So or outperform this. So that is the motivation of using DVR and other architectures. So just to show you that for different coefficients and different trainings for 2, 3, 4, 5, number 0, 1, 2, 3, you see that we have different improvements. So ACPR effective is the effective decrease in the leakages, 7.3, 6.95, 14.52. So then by that you make a system where you can do this learning based at what is the right point of the coefficients that you have to select to use in your system. And this is a very well explanatory example because I always rely on something that is visually makes sense. So maybe EVM and ACPR are not very attractive to the audience, but if you see the spectral regrowth, you see that without DPD, at this black colored one is the without DPD output. We are not linearizing it. And this red one is the input. And our idea is that we would like to make our input as close as possible to this red one. So there are two channels. So you have two performance, you have two references. one at the 900 carrier and then 800 megahertz. And then with the performance of the GMP and DVR, the linearization, you see that GMP is blue, DVR is green, and DVR is actually outperforming the GMP one. So it is very clear that DVR is performing better as compared to GMP at 800 and 900 megahertz. Okay, so for this, we have linearized the systems with different lasers at different lengths using different techniques, basically Volterra methods, CPWL, which is DVR method. Then we have feedback realization. We've done it for multi-channel DPD, and that is something that we have done for the performance enhancement using. Yeah, any question? No. Okay. So the next thing is the machine learning or deep learning based enhancement. So previously you were seeing behavioral model for enhancement of the performance. Then you saw the adaptive compensation. And now we are using deep learning or machine learning for increasing the performance. And the reason is that still we are improving, but there's still a chance to improve the performance enhancement in our Fronthauls. So in this part, we will see and we will revisit that what is ML, how it is working, and how we are utilizing it in our block. So I just put here the very simple definition that it is a field of study that gives the computer or machine the ability to learn without explicitly programmed. So you can compare here the traditional programming with the machine learning, that the reason the difference is at the output and the program. So you have the same mechanism, but instead of having a program here in traditional, you have an output, and then you train it, and then you have a program that does the system as an output that is performed. So machine learning has evolved over the years, starting from the electronic brains in the 40s by the perceptron. Then the XOR problem was solved in the 70s. We came towards the backpropagation, SVM, KNN, in late 2000s, and then finally in 2010, the deep neural network pre-training was given. So machine learning has evolved, and it has actually speed up every type of application that we have seen nowadays. So it is work. You can see the application of deep learning, artificial intelligence, machine learning in each perspective. And similarly in communication systems, this is a new techniques that have been developed with machine learning, and everything is being evolved. So I just put here a simple explanation that generally when you have, let me see, I don't know if it is, yeah, it works. So you can see that we have classification. So if someone is eating or taking a meal, brushing a teeth, so you have a label and you predict it. So taking the label and prediction for a simple examples of dropping or eating or brushing your teeth or moving. So you can do each and every labeling and prediction with regards to that. And similarly in communication, you can use the similar techniques to do the machine learning based applications. Yeah. So just to summarize that, we very well know that artificial intelligence enables machines to mimic human behavior. Then it's if you take a Venn diagram, the subset of the AI is ML, which is the statistical method to enable machines to improve experience. Then comes the deep learning, which is a subset of ML, making the computation of multi-layer neural networks feasible. So if you see comparison between the ML with deep learning, you have input, you have feature extraction, classification, and then you give as an output. Well, in deep learning, you just change this method of feature extraction and classification with the neural networks. So keeping this in mind, we actually took the same architecture of the linearization of our optical communication bench or Fronthauls system. And this is still what we are showing here, just a moment. This is still a radio over fiber. You have a laser, you have fiber, you have photodiode. So this is again a ROF link, the Fronthauls. But then you can change the methodology that you're using for enhancement of the performance. Instead of using GMP or DVR, let's rely on neural networks. And what happens if you use neural network to train the system and predict the coefficients that you were doing with the MP and GMP? So based on that method, using the deep learning, what we did is that we have a ROF link that we have seen always. We model it with the neural network, and then we train with the help of the labels X of n and Y of n is the output. And once we converge the system, we use the DPT neural network model, which is the inverse of this one, and we cascade the ROF link over here. And then X of n is the new coefficients input, and Y of n is the new expected one. So here, what we have done is that we used ADAM as the optimizer. We use mean squared error as a loss function. We use 6 hidden layers over here. Neurons per layer was 25. We used ReLU as the hidden layer, and regularization we used as L1. We also used L2 and dropout, but the best one that behaved with this type of system is L1. So based on this, giving you just a flavor that what were the values that we have used for our system, this is still a good question and a good point of demonstration and research, that what will be the exact number of neurons, what is the hidden layer type, how to optimize your system. But for now, it is hit and trial and some other basic, let's say, benchmarks that we use for training our system. So now the question is that you have previously seen that we have a generalized memory polynomial who performs like this. Then we have without DPD black one. And with neural network, with this DPD-based neural network, we actually outperform the performance of GMP, which is actually Volterra series method. And then with this green one, with neural network, we outperform GMP with this new neural network. If you see EVM, which was around 9% at the present for the type of laser that we were using, and that was around 4%. And then neural network is still giving you a value of around 3.8, 3.7, and the benchmarking or the limit is 3.5%. So yes, there is a lot of reduction in the EVM, but still we have not met the criteria set by 3GPP for 256 QM, which is 3.5%. That is true that 5 dBm is a very high RF input power, and we generally operate up to 0, or let's say over something here. It is just to see the efficacy, how efficient your model is, and how good it is performing with respect to 5 dBm. So if we are using 0 dBm, yes, it's good that we are around 2%, so we are good to go. But let's push our limits and try to linearize the system up to 5 dBm. So these are some of the further readings, because this is still an ongoing project and we're still working on the neural network and machine learning topics with the optical communication. So for further readings, I have just added some list of the papers that we just published in the last 4 or 5 months in order to highlight the effects that we're using with the help of neural networks and machine learning. So I think we can take a 5 minutes break, and then we can restart with the next topic of the deep learning in MIMO and the Fronthauls scenarios. Is it okay?
Yes, sir.
Okay.
Yes, it is okay, Dr. Smart.
Okay.
Slide 26.
Hello, Dr. Usman. Hi, Dr. Usman.
Hi, Dishant. Yes.
So it's not Zishan, it's actually Rizwan. And
Yeah.
thank you very much for presenting at FAST University. Your talk was very interesting, and the animations you use were also, explains the concept very well. So, like, my friend Zishan has a question.
Yeah.
Like on slide number 26.
Yeah.
So,
Let me show you.
Slide 26.
Yeah.
You're saying something about vector distance.
Yes.
Down of this line 26 number slide, I think. Yeah, this one. Okay. And why not to use the angle between two vectors? Because to the best of my knowledge, this angle will be much important than that of the actual distance or the magnitude of the vector. The original and I think updated or.
Well, I think that if you see the I and Q's, the input and quadrature, you have the magnitude and phase of the error as well. If you see here, we have the phase error, the phi, and then we have measured signal, and then we take the magnitude of the error. That is true that this is not the phase that we are computing, but that is the standardized, let's say, matrices for finding the magnitude of the errors. Why don't we find the phase of the errors? Because we are interested in, let's say, finding the magnitude response of the errors that will affect our system level simulations. For example, here if you see the EVM, you can also find the power of the reference with respect to the error vector. So this is like an accumulated version. For example, you can find the bit error rate or symbol error rate as well with respect to EVM. There is a formulation that you can find EVM, and that is equal to bit error rate also. So here we are finding out the linear time terms of error vector magnitude. Why didn't we find the phase? It was simply because that was the metric available in our signal analyzer at that time.
All right. Okay, thanks, Dr. Usman.
Dr. Usman, can you hear me now?
Yes, I can hear you.
Dr. Usman?
Yes, can you hear me?
Yes. And
Okay.
so, Dr. Usman, what I understand from your talk, like I'm not familiar with this topic much, like you are transmitting radio waves over fiber. And then there are two types of, you are listening? Can you hear me now?
Yes, I can hear you. I'm just taking out the block diagram. Yeah, you can please speak.
Yes, sir. So there are two types of nonlinearities, like electrical and optical. And then you are using a pre-distorter that you call DPD to model these nonlinearities.
Yeah.
And like the whole work is focused on modeling this pre-distorter. Most of the work is, and then you explained earlier that you use some memory-based techniques like GMP and memory-based polynomial technique to model this pre-distorter and to remove the non-linearities in the system. And then you, at slide number, I guess 37, you said that you are using only the error signal to train. Yes. So here you define some threshold value, or what is the reference signal here? You already have the reference signal.
Yeah, good question. So the point is that, let me share. The point is that the architectures that you have, MP, GMP, even the neural network, RPEM, whatever you name it, LSTM, whatever you will use, this will come as a part of the architecture that you will use over here. And obviously, this will give you a coefficients, and this will have an output that we named as ZP1 or ZP2. And then you compare the output ZP1 with the X1, which is the input, which is the ideal one, and find the error here. Now, this error has a reference there that we set as, let's say, there should be 10% of the X1. Right? So for example, if the value is 2.15 here, and after the training, the P1 is 0.5. 0.5 is greater than 0.5. So then your training has been worked. You will again perform the training with the new coefficients and update the coefficients until and unless you reach this point that has been set by the systems parameter that we have.
Okay.
So lower the error.
1 over G1. Is it a constant? What this block diagram? 1 over G1.
Yeah. So actually, in the ROF system, we have EFAs, the electrical amplifiers and optical amplifiers. So they actually amplify the magnitude of the response of your output, the system that you are performing. So that magnitude that has been, let's say, amplified, you have to bring it back to what it was at the original X1 over here. So then these general gain adjustments are done according to the floor of the signal that you have at the input. So they actually they always change. If you're using a 5 dBm of RF input power, maybe they are using 1 dB of gain adjustment. If you are at -10, maybe it is -15. So they're like automatically adjusted with the help of the input signals, signal floor that you get from the signal generator.
Okay.
So even if you don't do it, there is no effect because you are actually. For example, if you have a response of signal something like this and it is centered at 0, maybe if you don't do it with respect to the signal adjustment, it will have some offset instead of. So in order to give it an offset in magnitude, you bring it back by using the signal adjustment amplifiers, the gain adjustment, so that what you train, what you get at the output, because a very fundamental issue is that you have to compare your trained signal with the transmitted signal X1 and X2. So that should be in line with the magnitudes that you have with respect to X1. So maybe we can restart. If there are no questions, maybe we can restart.
Sure, sir.
Yeah. Usman, you're good to go.
Okay. So in the first part, we were seeing the basics of 5G, why we use 5G, why we are using the radio over fiber techniques. We were seeing the analog radio over fiber, and we actually proposed 3 things: the behavioral model, the Volterra methods of MP, GMP from DVR. We used canonical piecewise linearization with DVR, and then we used machine learning, deep learning. I just gave you a very brief crisp of using the deep learning neural networks for performance enhancement. Now, the next thing is the 5G and our Fronthauls scenarios. And this is the topic that we had involved in the project called Ultra Reliable Fronthauls Solutions. So let's say that now we are using still analog ROF, but we are not relying on the linearization of the systems. We're just looking at the Fronthauls experiments with using 5G NR. What you were seeing previously was with LTE, LTE Advanced. Now you are using 5G NR, which is the new 5G NR means fifth generation new radio. So it is a new signal. Its basics is from 5G. So what we are doing in a very recent work that we have started to do is that we realize an analog ROF. We use fiber wireless, which is actually MIMO, multi-input, multi-output antennas. We have fiber, which is the optical communication like radio or fiber. And then we have a wireless medium. So we are trying to mimic that. Once you have the fiber up to your home, then from that part of your broadband, you use Wi-Fi or whatever at the receiver end, at the user equipment side. So we are connecting the fiber with the wireless medium. So for that, we actually started the experimentation with the new radio, which is 5G NR, using Mach Zehnder modulator, which is the external modulation technique. We still have radio over fiber. So this block that you see, let me change it back to pointer. So this all is actually your radio over fiber. This is the signal baseband signal generation. You have modulations here, signal generations. You have the transceiver, you have the laser, fiber, and photodiode. And one thing is that this red one shows the optical signal domain. And then from this optical, this blue one is electrical. So here you have electrical signal, you have optical here. So you have to, when you work in this domain, you have to be very careful that which domain you are working. Is it optical? Is it electrical? Where you have the RF signal? Where you're using a baseband signal? What is the output? Are you using baseband? Are you using the image of the baseband in the undersampling? So these are the basics that you learned with the experimentation. So we are working with both domains now, optical, and then we have electrical. So now when you have the output, which is at the electrical domain, you have the transmitters, TX1 and TX2. Then you have receivers, RX1 and RX2 here. So what it is that you...
Sir, I have a question. If you use optical and then electrical, the bottleneck will be the electrical.
Yes, because if you have optical domain, you have already reduced the nonlinearities up to the point of optical, which is up to photodiode. And then you have electrical signal that you have to transmit using the antennas, like let's say the wireless.
Sir, if we have bottleneck of electrical, so it will be a benefit to use optical or no?
The problem is that if you use a wireless medium that I showed in the start, which was using the electromagnetic waves, which are the types of analog, and you convert them into digital, they cannot travel long distances. So that is the reason that we used fiber, so that you can reach a maximum distance. For example, we have reached a maximum distance up to here, and then we transmit that signal to a tower or whatever, the antenna, to the user. Let's suppose your friend or your phone or your laptop or whatever. So it is like trying to understand that what happens when you have the optical domain limitation and then you come towards electrical domain. And now you are merging the two things, the fiber and the wireless channels. So fiber is there, we have understood it, we know the understanding of the optical and electrical domains. And now the idea is that push the limits of the wireless link that you're using. So we are now relying on the wireless part, which is that you have already reached the electrical amplifier here, and you have the diplexer to switch between the TX1, the transmitter, and TX2. And then it behaves like a MIMO system, which is the multi-input and multi-output. So you have TX1, TX2, RX1, and RX2. Here I'm just using two receivers, two transmitters. So what happens is that this TX1 will interact with RX2 and RX1 simultaneously. And this TX2 will also interact with RX1 and RX2 simultaneously. So what we will have is that the famous Y is equal to HX plus N equation, which is the Y is the received signal, H1, this H are the channel matrices, X1, X2 is the transmitted one, and these are the noise AWGN, let's suppose, that we model. So now we rely that we have the signal generation, and mind you that we are using two signals here, X1 and X2. So we have 3 gigahertz, we have 850 megahertz RF4, 795 to 800 megahertz here and 23 gigahertz. So we have actually 4 signals, but we are using 2 at simultaneous points. So because TX1, TX2 will interact with 2, and then RX1, RX2 will have a response from TX1 and TX2. So overall, there are 4 channels that you realize. So we have 4 RF signals using. And then another question can be that why the VSG2, which is the signal generator 2, is giving a window of 795 to 800 megahertz. Why you are not using a fixed value? So we will see that why we are trying to mimic from 795 to 800, because the other LTE advanced that we are using at RF4 is 815. So we would like to move RF2 from 795 to 800 so that we can see that how much is the interference when you bring 800 between 815 to 15 megahertz. If you take it to 795, you move from 795 to 815, which is around 20 megahertz. So we would like to see that how interferences see in the electrical spectra. We will see in the next slides. So the idea is that we are mixing the 5G NR signals with the 5G transceiver signal, which is 3 gigahertz, and then at the VSG2, we have LTE advanced at 815 megahertz. So this is the overall picture of the setup, where we have the fiber, we have the wireless channels, that is the MIMO, which is the MIMO 5Y, MIMO, multi-input, multi-output, fiber wireless. So you have fiber, you have wireless, and then you're trying to see how is the performance of the system. And here we are not using any linearization up till now, because we are still realizing and understanding the results that we are getting. So we try to see the 5G transceiver received waveform, which is orthogonal F and G, FDM, frequency division multiplexing, and we have a limit of 3.5% for 256 QAM. Mind you that we can actually use up to 1024 QAM, but we are generally using 256 generally, because in the previous slides you saw 256 QAM, so it is better to benchmark 3.5% limit. So here you can see that with the received power from -48 to -32, you see a very sharp 7, 10%, 9%, up to 2% of the values. And we are actually not linearizing the system. So it is just to see that how are the results when you use the 5G NR multi-band signals in this scenario. And also, the problem is that the degradation that you are seeing is due to the filter's nonlinear response because of the OOB. You have the out-of-band emissions because you are using 815 megahertz, you're using at 800 megahertz or 795 megahertz, and then 23 gigahertz and 3 gigahertz. So you're using FR1 and FR2, which are the frequency ranges below 6 gigahertz and above 6 gigahertz. So there will be the out-of-band emissions used for the filter's nonlinear response. And when you see the electrical spectrum at the output of EA, when you use the 3 gigahertz and 23 gigahertz, the good thing is that we are able to isolate 3 gigahertz and 23 gigahertz carrier signals because we were transmitting at 3 and 23. Now, the problem is that with 3 and 23, we are able to get a very sharp peak, which we can see. But the problem is that we have some noise floor here. And up till this point, this is fine, but then this is starting to grow, which makes me realize that maybe if I push my frequency above 25 or 30 gigahertz, it is possible that you will start to get some rising and sharp peaks of this noise that is coming. And that is because of the interferences between the signals that you are having. So that is one point that needs to be studied and needs to be that we are evaluating, that how we should adjust the frequencies if we have to go above this frequency range. Now, if you see the EVM versus the optical power for the 50 megahertz, 200 megahertz bandwidth, and 400 megahertz bandwidth, and you can see very clearly that previously when we were seeing the curves for the LTE and LTE advanced in analog graph linearization systems, the maximum bandwidth was 20 megahertz for the LTE. But here you can push your bandwidths of the signals up to 400 megahertz because this is 5G NR. So this is good that you have a very higher bandwidth of the allowed bandwidth to carry your data. So here you can see that still without linearization, For 50 megahertz, you don't need linearization, and we can see that 3.5% limit is already meeting here, and you're good to go here. But then if you have 400 megahertz, you are not meeting the criteria of the 3.5%, and also partially 200 megahertz bandwidth is also not meeting the criteria. So in that way, if you have to use 400 megahertz bandwidth, and as 5G is evolving, higher the bandwidth will be, the utilization will be higher. So this is true that for 400 megahertz bandwidth, these results are not meeting the standardization. So that is the research that we are employing, that everything is not good. You have good results, but then you have to improve that. That is not according to the standardization. So there is some work to be done here to improve the standardization, the performance, maybe using the linearization techniques and using neural networks, for example. The point is that for now, everything is moving towards the AI. So it is a new trend to use everything with ML and AI and deep learning. So maybe in future, we will just rely on using the deep learning technique for improving the standardization for 400 megahertz bandwidth. And now comes the point that, as I was telling you, that we had 795 to 800 megahertz bandwidth for RF2, the frequency RF signal at VHD2. And the other was, it was moving. The reason is that because you had RF4 at 830, so what we would like to do is that we would like to move the signal between the range so that you can see that how the spectra looks like. So if, for example, if you have a spectra where you have the frequency offset of around 15 megahertz, then you see that when they are overlapping each other, the EVM is around 10% for 5G NR and LTE advanced both, which is very high. But if you move more than 15 megahertz, like you go beyond 15 megahertz, so then you can see that you have a very sharp curve and you are not overlapping the signals. And in that way, the EVM starts to decrease. So you have to be very cautious and selective that when you are intermixing the 5G NR with LTE advanced and using multi-band channels, because they are good for the realization and they are better in performances and they offer high data rates, the selection of offsets is very important. And what we have observed is that for offsets less than 15 megahertz, the EVM is high, and this is because of the interference between the 5G NR and LTE advanced signal. And for offset greater than 15 megahertz, EVM is less, and it means that the coexistence is affected with respect to offset, but still they can coexist. So this actually realization or the topic of the research is to see the coexistence of LTE NR with 5G, LTE advanced with 5G NR. So that concludes that they can coexist. You can have good results. There are limitations for 400 megahertz bandwidth, but then also an important factor is to see the coexistence between LTE advanced and 5G NR for a particular offset. So these are some of the readings that you may see if you are interested in seeing these results. So just to give you an idea that the 400 megahertz bandwidth, the resource blocks are 1700 and the megabits are 1700 and NRB is 264. And we are using 5 kilometers of single mode fiber length. So the length is actually good enough to do any type of communication. So now comes again the deep learning, and we just move aside from the optical communication a little bit to give you an idea of MIMO, because we were talking about fiber wireless, and then in the wireless domain, we were talking about multi-input, multi-output, where we were seeing that we have y is equal to hx plus n based equation, where we have transmitted x and received y's. So we can also use let's say deep learning in those techniques. So here you can see that we have y is equal to hx plus n, and what we are trying to do is that y is the received signal, we have received a signal with respect to the number of receivers. This is a complex type. Then the X is a transmitted signal, where its type is dependent on the number of transmitted antennas, and H is the number of channel matrices that we receive with respect to NR times NT. So this is the overall structure of Y is equal to HX plus N that we were talking about. So receiver, channel matrices, noise, and transmitted. So we are not talking about fiber now. We are just talking about the wireless medium here, that we just isolate the received signal and the transmitted signal in the wireless communication to see how we can use deep learning here. So the idea is that generally we have estimation methods like minimum mean square error, maximum likelihood, successive interference cancellation. There are different type of receivers that you do. But what if we use deep learning methods to train and get the transmitted symbol and detect what we were doing with the basic of channel estimation that we are doing here? So if you have a transmitted signal X, you transmitted, you have a received signal Y, and then you would like to estimate that what was the transmitted, what is the received signal with respect to Y that you got as X hat. So the idea is that you try to use the channel H and Y. You don't know X, you just know Y and you know H, and you try to find out what was the transmitted vector, which is the X hat. This is the channel estimation, or let's say the detection that we talk about MIMO. So if you see it in terms of deep neural network, you have Z of N, which is the input, and you expect that P of N will be output. So Z of N is Y of N, which is the received signal, and H of N, which is the channel matrices. And here we have 4 inputs, which is the real and imaginary, real and imaginary. So real part of Y output, imaginary part of Y output, real part of H matrices, channel matrices, and imaginary part of matrices. And then you receive the P of N, which is the m-dimensional one-hot vector. So what is M? M is the order of modulation. If you're using 16 QAM, it will be 16. If you're using 2 QAM, 4 QPSK, BPSK, 64, or even 256, so that will be actually the m-dimensional one-hot vector that you receive over here. So what we do is that we test the network containing the probability that transmitted symbols equal to corresponding entry in the constellation. So you see to find out that what was it transmitted as compared to X that is not part of the DNN setup here. So I just add here results to visualize and discuss just a part of the results here, because maybe it is interesting for the people who are working in the deep in the deep learning and neural networks. So I have added here different sets of data. Let's say we have 100K, we have 200K, we have 500K, and up to 1 million data. And there is regularized data and not regularized data. So you know that when we have the overfitting or underfitting, it is must to perform the regularization. And here I have added the dropout setup, because that is the one that was working the best. We have the batch size of 16, 32, 64, 512, 1024. I mean, this is the size of the batch size that we have used. And then you can see 1 million T, 1 million V. So this training data and validation data. So for example, if you see the 100K training and validation, you can see that the validation is, training is below the validation. So you have to perform the regularization. And if you see the regularized 1 million, for instance, the orange one, you see that they are close to each other. So you have actually met the regularization here, this yellow line, 1 million T regularized, 1 million V regularized. So they are close to each other over here, this one. And without regularization, it was this one. The V is orange and dotted orange is the 1 million training. So the point is that if you see the symbol error rate for this structure at up to 30 dBm, and we're training at 30 dBs with 16 QAM, you see that this blue one, this blue, This is actually the minimum mean square error based receiver, which is a traditional receiver, the benchmark receiver. And we would like to outperform this blue curve. For instance, we want to perform better than MMSE. We can only sell the idea that machine learning or deep learning is performing better if we can perform better than this blue curve. So for instance, if you see the 1 million regularized data, this yellow or orange, you can see that for a training up to 30 dBs, up to 25 or 27 dBs, the performance is better. For example, you can see a very sharp kink here that from this blue curve to this orange one, you are able to perform better than the blue one here. So this means that there is a lot of potential in deep learning to outperform this blue curve, the minimum mean square error-based receivers. But the problem is still here that at the last point of training, which is 29 or 30 dBs, the blue curve is better as compared to the deep learning curve. So it means that still the deep learning based structure that we are using, there still need to be adjustment and optimization so that we can also beat or outperform our minimum mean square error benchmark receiver with the deep learning method at 30 dB. And for now, we are not able to do that. And we would like to do that. So that is the point, that we are able to outperform this in this part to 20 to 25 dBs. And the questions are, can we do that for 30 dBs or higher? Can we push our deep learning based networks to perform better than that for 30 or above? So these are some of the points that needs to be answered and needs to be formed. But still, up to now, even if you see other people who are working not on the AWGN, we have two types of channels: AWGN, additive wide Gaussian noise, or the Rayleigh channels. So this is a Rayleigh channel, which is the real channel where you have the all the realizations, you have the scattering, and you have all the other things. So for Rayleigh, can you beat this 30 dBs performance of the MMSE based receiver? If yes, then deep learning is good to go. And this can beat for sure, but you need to understand that we have limitation in terms of resources here also. 1 million data is a huge data as compared to when you need to train and validate it. And then if you see this number of the 1 minus accuracy, you can see that we are up to 10 raised to the power minus 2 here, which is the 0.009. This value is here, 10 to the minus 2. And here you see the 10 to the minus 2 and this the point up. So we can actually very clearly see that there is no cheating. 10 minus 2, this point is actually intersecting with the symbol error rate as well. So by looking at the 1 minus accuracy, you can also have an idea that symbol error rate is fine. But even at 100 or higher training epochs, you cannot see any improvement in the 1 minus accuracy. So the question is that, do you need to change the deep learning or deep neural network? You need to optimize it, or you need to change the training point, because this is also an important point, that you're using 30 dB and you're training all your link at 30 dB. And that is the only point where it is not outperforming it.
Excuse me,
So,
sir.
yeah.
Usman, I have a question. Which architecture you are using? Like
This is deep neural network.
Like number of layers. Have you shown the settings? Like it's like simple deep neural network or CNN architecture? Which type of architecture?
It's just a simple DNN.
Simple DNN. Okay.
Yeah, we are just using I think 3 or 4 hidden layers.
Okay. And then you generated this data set by your own, or is it publicly available data sets?
No, we generated it by ourselves.
Okay, okay. And then this axis shows the number of epochs.
Yeah.
Okay, okay.
And the idea is that keeping it simple as possible. SAP, that you use less than 5 layers. I mean, if you go to a very complex system, like you were saying, using the CNN or other things, for sure we can beat it. But the point is to keep it SAP and then outperform it as compared to MMSE, which is this blue curve. So benchmarking the blue one and improving this is the point where we are still struggling to do it. So there are some points that we have done in simulations, and I have some good understanding that if you change the SAP configuration, you can do it. But then we don't want to make the complexity higher at the, we can have the training complexity higher. For example, 1 million is a lot of complexity. It is a lot of overhead, but we don't want to have an overhead in terms of the neural network configuration. That is because of some overhead due to the settings of the user equipment side that is generally in the system level. So that is the limitation point, that you cannot have more than some number of layers and hidden layers and all the architecture.
Okay, sir.
Yeah.
Thank you.
I have a question.
Yeah.
Okay, just let me change these.
Okay, I think here in this deep learning, we have a challenge of data, the data size. How much data can we generate for this particular problem or for this particular issue to apply a deep learning model or any model? I mean, how much feasible is to generate a data of, let's say, of records of thousands, millions, or maybe in this domain, is it easy to generate a set of millions data elements?
So actually, it depends the resources that you have. If you have the data servers, 1 million data can be generated in, I think, less than 1 hour. But if you're using your own PC, for example, for instance, if I am using my own 40 GB RAM laptop, it can take up to 18 hours of generating the data, and then testing and validation is a separate thing. So you have to push your limitations in terms of generating, but it depends how much you are spending on the resources. If you're using the data servers, then it is not a problem. 1 million data can be generated in almost 1 hour. And you have to generate it once. You don't have to generate it every time. So.
Okay. And even using my personal machines, hopefully in a couple of days, we can generate millions of records in this problem. So we can try a more complicated neural networks, or maybe increase of layers to get the accuracy, because we have a huge data for deep learning, I think.
That is true, but there is one thing that needs to be understood, that the output that you are using in this classification system that we have built it's a classification type. So you have m to the power of n as an output. And if you have 2 receiver antennas, 2 RX, and the m is the number of QAM, so imagine that you have 16 to the power 2, that is 256 classifications, or 256 one-hot encoding vector. Now, if you have 256 QAM, or let's say not 256, but you keep it simple as 16 QAM, and you have 10 RX receiver antennas. So just imagine that what will this number be, right? So that will become a very huge number. And that is the limitation of the system, that the output depends on m to the power of n, and n is the NR, the receiver antenna. So modulation, this is by doing classification. You can also try the regression method, and with the regression, this can be solved, this problem can be solved. But then comes your point of creating the data. So yes, I think with the new advancement, problem of creating the data will be solved. It's not a big issue. But then in this particular setting, this is a big issue, because if you are dependent on the number of receivers with modulations, then just imagine what this number will become when you will have multi-user MIMO, maybe 20, 30, I don't know. So still, this is an ongoing, let's say, point of interest to how to move around this point.
Sir, what or how many features are there in each instances?
So actually, it is all modulations. So you have like received constellations at 16 QAM. You will have 16 received features. So there are 16 numbers, and you have to match those numbers with respect to the transmitted signal. So they carry each I and Q, so it's real and imaginary, but they are just numbers.
Okay.
So, Dr. Usman, have you tried any pre-trained model? Because what I think 16 days to power 10 is, of course, computationally complex, but there are systems, scientific computations can be much expensive than this, and it is achievable. Like training millions of parameters is quite normal nowadays. So,
but the thing is that we are thinking from not only the research point of view, but actually in deploying it in the standalone receiver equipment. So the receiver equipment UE has no memory, so you can have some, you can turn around, but already if you're talking about non-standalone or standalone, you have to be really specific with respect to that point. From point of research, yes, this is a good point of moving ahead, but from the point of view of deployment, this is still a big issue, and that is the problem, that when you come to machine learning or deep learning in the equipment side, you need to move around. For example, if you talk about the 6th generation air interface, that will be based on machine learning or deep learning. But then will you be able to do all the transmission chain and receiver chain with machine learning all of a sudden, or over the 10 to 15 years? It's still a big question.
So, Dr. Usman, one more thing, like you have been working in this area of communication, but we don't have much knowledge. So I want your words, like, will it be better to use a deep learning model or an hand engineered model? Which model? Like you have some domain knowledge. If it's of course, in deep learning, if you have some domain knowledge, we must start with a simple model. So I think, will it be better to go in a direction that finding some critical features and then designing a model? What do you suggest?
I think the best thing is to start with the basic, just the simplest model. Starting with the neural network is the best. Then you can move to a CNN, even LSTM. But starting with the simplest is easy to understand how things are behaving. So, and then if I understood well, your question also asks that, is machine learning or deep learning the future of communication? So I think partially yes, because all the stakeholders, Huawei, Nokia, Ericsson, all the big names, even from the industrial side, they are working on machine learning, and they propose to use deep learning based solutions in the next generation. So this will be the future. How, it is still to be figured out if to realize it, but starting from today, after 5 to 10 years, we will be using deep learning, I'm sure, or machine learning or AI, whatever you name it.
Many application areas, this will be true.
Yeah, I mean, for example, I've shown you 2 examples now. We used it in optical communication, which is a very new concept of using deep learning. Here I've just used it to linearize the system. But you can also try to use this machine learning, not the deep learning, machine learning, like SPM and KNN and those type of structure that we have used to predict and use the optimization of the network of the optical communication system, where to operate, which RF input power should be operated, when you can have a glitch in your system. So based on that system, you can optimize your link by using this communication system. And then for this wireless communication, in MIMO, you can find thousands of papers where people are predicting that they have outperformed the minimum mean square error receiver or MMSC or ML receivers. Why? Because they are using the AWGN or whatever, so they are still able to outperform those things. So future is ML and deep learning for sure.
Sir, could we have this data so we can do some experimentation on this?
Sure. I can arrange this data. It is not a problem.
Okay, thank you, sir.
Okay, so maybe we can move a little bit again to the other side of the communication, which is, I think, the second last topic, because the next is more interesting about the embedded system, but it is better to move in a sequence. And previously you were seeing analog radio over fiber, then we talked about the linearization, where we talked about the signal processing aspect, where we used digital pre-distortion, behavioral model, machine learning, GMP, Volterra series, and then machine learning and deep learning. And then because we talked about fiber wireless, so we came towards MIMO, and we talked a little bit about deep learning communication aspect. So now comes the digital radio over fiber. And this idea is that when we were using the analog radio over fiber, we performed well, but with help of linearization system. But instead of using the analog, why not rely on using the digital form? So we have the ADCs, the analog digital converter. We have digital analog converter. Other than that, all the communication system is similar. So we have the same laser fiber photodiode, but we have a signal processing circuitry like ADCs and DACs to do that. The reason is that there is a motivation. It is like a trend that once you have analog, the companies say, no, let's invest in digital. So everyone starts talking about digital thing. Now, for example, everyone is investing in deep learning. Even things are not very clear, and motivation is there, but the things are not clear, but everyone goes towards that side. So there was a trend in late 2000s where digital radio or fiber was being utilized. And for sure, it has a lot of advantages over the analog one. And one of them is that you can use it up to hundreds of kilometers. So you don't need to care about anything. You don't need any linearization. You just used it with the help of the digital circuitry in the digital ROF, and you are good to go. Now, this is good that there is no nonlinearity issues. You can use it to hundreds of kilometers. The data traffic is a lot. But then the problem is that these resolutions of the ADCs and DACs, they will increase the precision of the system. And as we know that 2 to the power n, so as the resolution increases, the cost will increase as well. And that is the limiting point for the digital one. But just to show you that how you compare it with the analog one, you have the analog system, analog ROF, where you have no circuitry, just the laser, the fiber, and the photodiode, and then there's the performance evaluation. While if you see the digital one, you have digital signal processing kit, DSP circuitry, you have ADCs, you have DAC, then you have again DSP. So you have a lot of overheads in terms of implementation. But just to let you compare the results, that if you see the fiber length up to 70 kilometers, the analog ROF has 20%, almost 20% of EVM, while digital ROF has around 2 to 3% of EVM. And because we're using 64 QAM, so the limit is 8%, not the 3.5%, because it's not 256 QAM. So you see here that even the constellations are very noisy at 70 kilometers, while for digital, they are very clean. So the point is that for digital, the performance is great, even if you see the EVM versus RF input power. When I talk about RF input power, it is the input power that you want your system to use, at which the carrier frequency is modulated. So if it is 8% here, if you see the limiting or the distribution from -20 to 0 dBm is the power for the analog, while for digital, it is -20 to 8. So you have actually increased the distribution of the power that can be utilized for the digital one. And yes, digital performs better than analog, as you can see with these results. Just to give you an idea that this is the way we model it. When we have the quantization, when we have the ADC, it means we have the digital signal oscilloscope, we have the quantization, we have the pulse spectral generation, we have this undersampling at 128 megahertz, the biasing, the fiber, laser, photodiode. Then we have again the correlations, the DAC, where we have the zero order hold, signal reconstruction, and then signal analyzer. And then you can see the amplitude, voltages, and RF powers that we have at 2.4 and 3 gigahertz. This is how we validate this system. So this is just a comparison that because we have a concept of undersampling in digital radio fiber from digital signal processing, DSP is just undersampling, that you have images of the carrier frequency. If you have a 2.4 gigahertz carrier, you can undersample it by using the band pass sampling concept. So I will not go in detail of band pass sampling because it's just images of the system that you have. Because generally you see the channel and you say that the carrier should be the carrier should be greater than 2 times of the fs. But actually there is the other side of the equation as well that is generally ignored, and we don't see that. So that is the undersampling or bandpass sampling part. That is that you can still have the carrier which has you can have the images of the carrier at those particular bandwidth. So that is why you see that 100 megahertz is the image of the EVM at 2.4 gigahertz of carrier frequency. And we just want to show that the 100 megahertz undersampled image of the carrier has performance better, because lower the carrier frequency, you have less interferences. So maybe I will just pass on. Just the idea was to show you that analog digital has better performance as compared to the analog one. And now comes the more interesting part, which is when you see the communication or any aspect, you do the simulation, you do the analytical modeling, you do the experimental realization, and the end goal is to prototype it, make it on an embedded system or whatever you name it, and then sell it to the market. So this is the real-time implementation of Sigma Delta radio over fiber, and that was done on FPGA. So before I go into the detail, you have seen analog. We saw the linearization is required. Then we saw digital radio over fiber. It was performing better. But then the problem was the cost. And the cost was because of the resolution of ADCs and DACs. Because higher the resolution, higher is the cost of the system. Now, in order to decrease that cost, there is a system that we've developed known as Sigma Delta radio over fiber. So what it is actually a 1 bit of ADC. So because the issue in digital was the cost of the ADC resolution. So if you just use 1 bit of ADC, you don't have issue of cost. So that is the concept of using Sigma Delta modulation, that you have 1 bit of ADC here. But the problem is that we know that if you remember your digital signal processing slides of the sets that you used to study in undergraduate level, we have that staircase which shows that with the lower the resolution, higher is the quantization noise. So if you have 1 bit of ADC, the quantization noise or the noise floor will be very high. So what we do is that we have a band pass filter, so that the quantization noise that comes due to the higher low level of 1 bit of sampling that can be reduced by using band pass filtering. So that is the overall concept, that it's still analog radio over fiber, but we have amalgamated the use of Sigma Delta modulation. So by using 1 bit of ADC, there is no need of high cost, and it is very cheap. And because this is 1 bit, so the problem of quantization can be solved with band pass filtering. So just giving you an idea of how the experimental setup looks is that we have the input and quadrature baseband signals. We do the Sigma Delta modulation by using the second order STM modulators. I didn't put that slide of what Sigma Delta modulator is because it's generally known to everyone that how it performs, but it is more mathematical, where you have the signal transfer function and noise transfer functions. You have the integrator. So I just considered that everyone knows how it looks like. So we have Sigma Delta modulation and we have frequency up conversion. And then again, we have the laser, we have fiber, and we have photodiode. So 1 bit of ADC, the frequency up conversion, creation of this INQ was done on Xilinx Vertex VCU108 FPGA board, very sophisticated board. Sorry. So then on the remote radio head side, you have photodiode, you have low noise amplifier, and you have band pass filter. So with this band pass filter, you will remove the quantization noise. And that is the snapshot of the FPGA, and then you have a board where you are using 4 channels to realize and see how the Sigma Delta modulation and radio over fiber as together works. So that is the experimental setup. And then at the end, I just put analog, digital, and Sigma Delta results. That you saw that analog has this result. Then we had digital, which is an expensive choice, but it outperforms analog one. And then we have Sigma Delta, which is amalgamated version of analog and digital, but with 1 bit of ADC. And this is actually surprisingly better than all of these options. And that is the best option that is we have at the moment for the front-haul communication. If you see the eye-opening penalty or the eye diagrams, so you can see that the eye of the sigma delta off is very clean. You can see here, while if you see over here for the analog, it is actually closed, and here also you can see a little bit of point. So sigma delta radio fiber is very clean in terms of eye opening penalty or eye diagrams. And then if you see the ACLR, the leakages, analog has around minus 20 dBs as we were seeing previously. So mind you, there is no linearization in this figures. Just analog, conventional digital, conventional sigma. And then you can see that the sigma delta is again performing better than sigma delta. That is why at the end we prototyped at FPGA the sigma delta radio fiber for the application scenario. And if you see the baud rates with respect to 10 kilometer, for instance, you see that at 400 mega baud rate, you have 10 kilometers, and the loud bandwidth is just -5 and -6 dBm. Then this is when the EVM is less than 3.5%. So for less than 3.5%, these are the limits of the powers that you can input into your system. So for 5 kilometers, you have a bigger range. For 1 kilometer, you have bigger range than even 10 kilometers. But still with 10 kilometers at 400 mega baud rate, still there is an input which will give you less than 3.5 EVM for 256 QM. So this is a chart that we have developed that can be helpful to other people who are using these technologies. So these are some of the further readings that can be seen if someone is interested in reading this work and want to work on that. So the next point is, I think, most interesting, which is the collaborations and thesis topics, or let's say some topics that can be interesting for some people. And then obviously there can be more topics once we discuss. There will be more topics that we can have work mutually. The first thing is machine learning. So I know that there are expertise of people listening to me in deep learning and machine learning, and we have some understanding of the optical communication. So we can really bridge together the concepts of communication with deep learning or AI or machine learning. So for example, if we talk about the radio fiber communication, where we were using the neural network recently for enhancing the performance. So we had this particular flow of diagram where we had MP, GMP, and neural network. And then we believe that we can actually push this neural network to perform better than this particular performance. And the question is that how? So this can be a particular problem that we have the data, we have the system, and first thing is to model it, for example, on the simulation perspective, or we give the data to you, and then you try to beat this results of MP and GMP with the neural network. The other thing is that you have this particular performance with neural network. And in this form, you can actually understand that can you beat or can you outperform neural network with this yellow curve? Can we get that? So this can be a good point of understanding or doing work together to have an understanding that you realize a neural network or another system based on artificial intelligence or whatever you think of, and you outperform the performance that we are getting right now. So that will be a very, let's say, a very solid work that we can do. And the problem with the machine learning and deep learning guys is that they never publish the results that are not good. They always show the results that are always the best. So you never know what was the struggle, what was the way they got it. You just see the paper when they have the best thing in the industry. So this is something where we have to struggle and see that how we can. I mean, this is good enough, this is better, but then we always want to reach this point. Maybe we cannot reach here, but we can eventually decrease something with respect to what we are getting here. And then this is a work that will keep going for many years, because this is just single channel. Then we comes with the 5G NR, because you saw MIMO, fiber wireless MIMO, and we saw that we have different, let's say, new radio signals. So performance of interference will be higher. So you start with neural network, and maybe you start with the performance of MP, GMP neural network or something like this. So this is one of the topic in my mind. The other topic is that in the Sigma delta radio over fiber, you were seeing that we have the Sigma delta modulation here. And this is the ROF link. We have oscilloscope, we have bandpass filtering, and we have performance evaluation. The problem is that this bandpass filter that we add, this adds, let's say, phase and amplitude noise to the system, to the radio, to Sigma delta radio fiber. So we can have something like a pre-BPF, like a pre-bandpass filter, or like a post-bandpass filter realization, so that we can actually negate the effect of BPF that comes into the play in the Sigma delta radio fiber. So I didn't add any explanation more over here that what it has to be done, because we were trying something like adding a post or pre-BPF for amplitude and phase noise reduction, but that needs to be, I mean, it's a full-fledged thesis topic, so I didn't add things that are like in the air for now. But this is a good solid work that you can reduce the overall system noise figure by having the amplitude and phase noise reduction from this pre-BPF. And industry is very much interested in this work, because Sigma delta radio fiber is being used a lot in marine applications, submarine applications, and other things. The other thing is 5G wireless communication and health effects. And recently, as the advent of COVID-19 and other things, health hazards are being seen as the most important thing right now in the market. And if you search the web of sciences, you can find out that in last 5 years, the most thing that has been linked with 5G is health. People have searched about 5G appeal, health hazards, COVID-19, radiation, myths, whatever. So here you see that there is a lot of interest in this topic, that what are the wireless communication or 5G communication health effects, that how it can affect us. And there are a lot of important organizations in European Union and all over the world that are running the campaign 5G appeal against 5G. And recently in 2020 late, we had published a paper, a very small understanding of the things, and we tried to defabricate the myths that they have put around the 5G. So I have understood that still it needs to be done with a technical point of view, by seeing the experimental and using the deep learning and whatever neural networks to see the effect of 5G communication with respect to health hazards. So for example, what people have been claiming is that you have a remote radio head or a base station, and then this radiates the electromagnetic radiation, and that can affect your body. It can affect your chest, head. Then people have been claiming that even the mobile phones that you use, it can, sometimes people have charged it and it sparks up and it blows off, and 5G, this is to 5G. Even people have, even in countries like UK, the remote radio heads, these base stations were burnt because people thought that 5G is spreading COVID-19. So, and I am not joking, this is really, you can see on the internet that this has really happened. So this is something that can be done. And then one thing that is true, that there are electromagnetic radiations for sure. Their radiation spectrum is low below the X-rays, so it cannot really expand or let's say affect the body, even if you use it up to 24 hours a day, if you use all the time. But then still it needs to be debunked with in a technical way. So studying the electromagnetic spectra using the system level studies in these things can be a very good point of view to do this very novel topic, because there are very, very less people. I think there are 2 or 3 research groups all over the world who have started to talk about these things in a technical way. So that is one of the topic that is in my mind, and we have really started to work on it. So that can be a good idea to propose it and work on it. So other topics, because my background is from optical communication, so I cannot really leave it. So I always think to do something in it. So there is Keysight Technologies ADS behavioral modeling project proposal for the ROF. Then we have recently a collaboration with the Technical University of Istanbul, where they want us to do the image processing of some pictures of some animals, where they want to learn the classification of for some particular diseases. So there's a machine learning project for the image processing. And then what we saw as a fiber wireless MIMO system, there can be application of machine learning to that as well, where you saw the deep learning MIMO and all those stuff. So these are some of the topics that are in my mind, and then I would like to thank you for your attention, and thank you for hearing me out. And I think that there are some positions available. You can just reach me out and we can have discussion about that. So thank you very much. I think the floor is open for the questions.
Dr. Hadi, I have a question. You did not try machine learning based algorithms for DROF, yes? Did you try that?
Can you say again?
Did you try the machine learning based algorithm for your DROF, digital ROF?
Oh, no, because the reason is that digital ROF is already a very expensive equipment, and it had a good improvement and a good realization results, if you see in this result. So why not? The reason is that as in the start, I showed you that the legacy infrastructure means that analog ROF is already available all over the world, widely spread. It is all over the world. So if you have to improve something in digital, it will not sell, because digital ROF is not widely spread in the world, in the industry. So if you try to improve the performance of digital ROF, first you have to deploy it, and then after deploying comes the part of improving it with the machine learning or linearization, whatever. So the idea was that if you have analog ROF, which is already in the passive optical networks and in the FTTP or whatever you name it in the world, it's already widely spread. So the idea is to utilize that widely spread infrastructure and then improve the efficiency of the system. That is the reason we didn't apply anything on it. Even for Sigma Delta radio fiber, we have not applied it, because that is a very new technology that we are still working on, and it's not available in the industry. I mean, it will be available for the commercial usage, but for now, people are relying on analog ROF.
Dr. Usmana Hadi, I am Rizwan Qureshi, and I would like to thank you for such an interesting and insightful talk. It was a pleasure listening to you, and many of my colleagues are interested in research collaboration with you, like in the field of performance enhancement for machine learning and image processing for machine learning, and then how can we use the pre-trained deep learning models. I think these are areas where we can collaborate a lot, and like the young faculty, especially the young faculty, is interested to work with you. So
I think that will be great, because we already have collaborations with NUST, with KFU IT, then also with the JIK. So I think that will be great to have students and faculty members to collaborate and write some financial project. So I'm looking forward and always open for the collaborations.
That's great, Dr. Usman Hadi. And will you share this presentation with us?
Sure. I will email
to
CPT and I will CC it to you as well.
Okay, thank you very much. Thank you, sir.
Thank you, Dr. Usman.
Thanks, Usman. Dr. Usman. I'm Ishan Khan, and here a part of faculty. My area of working is on medical image analysis using machine learning and deep learning. So it's a pleasure to have this presentation and learning about the 5G and machine learning on these network data or these 5G data, and motivation to for this collaboration.
Yeah.
Thanks.
Anyone else who wants to ask any question?
Yeah, and sorry, just a comment to Dr. Zishan that we are very new to this medical imaging and those type, because we have worked previously with the FNIRS and this data sets, but we are more focused on the communication side. So it will be great to have some expert working on the from the side of biomedical and those type of image processing side.
I have a bit working experience on medical images.
Okay.
Challenge was a bit different, but at least images were medical images, RGB images, and
Okay.
problem was classifications.
Great.
Assalamualaikum, Dr. Thank you for a great talk. I'm Mohammad Waqas Sheikh, and I have joined you a bit late. Sorry, but the point of machine learning for image processing and application in medical domain is basically my interest.
Mhm.
And as you told that the medical side or the hazards related to the 5G, this can be done with machine learning, and we are interested to work with you, to collaborate with you. This field really is interest for me. So inshallah, we will have discussion on this with you in the future as well.
Sure, and let me just make a comment that it is a very novel site. So there is a lot of let's say things that can be done, and you have, let's say, you have very freedom to do whatever you would like to do in doing a lot of things, because as you all know, in academia, even in industry, if you have done something and if it is not according to the people's standardization, generally you don't make a very good impact. So here the floor is open, so I think that can be a very good project for collaboration.
Thank you, sir. Thank you once again.
Thank you.
You shared something about FPGA. So you are also working on hardware.
Yeah.
So you are designing the embedded system for these communication platforms.
So this was a project with the Nokia Bell Labs in US, and I was the visiting researcher there, and we realized the FPGA-based systems there. And the idea was that this is a new technology, which is sigma delta radio fiber, and then you have to prototype it on it is like a standalone system. So you cannot have a signal generators and analyzers and everything with the application where you have to implement it. So just you have a embedded system, RTOS or whatever. So we had understanding of FPGA. So we implemented let's say the standalone frequency up conversion, sigma delta modulation, and IQ signal baseband generation on this part, and then prototyped it and with all the other equipment. And that was done for 4 channels, because VCU 108 allows you to have 4 channels of transmission at a single time. So that is still a very good. Yeah,
I think that's a very interesting research topic as well, because many people are using FPGA as hardware accelerators for deep learning model as well, and this is very new. So,
yeah, but the point is that there are a lot of things that has to be done. I really like working in embedded systems. There is another faculty member from KFU IT who is working with NCP, National Center of Physics, and they are really using the embedded system. So there's a lot of scope in this work as well. But unfortunately now on embedded systems, the scope is still there, but more towards the military applications and that side of things.
Yes. So once again, thank you very much.
Thanks a lot for hearing out.
Dr. Usman, we will let you know, and we will discuss with you if we can have a meeting in near future.
Sure thing.
Thank you.